Hey everyone, today we're going to talk about the last chapter, section 5.1 specifically. This deals with exponential functions. So we're going to switch gears a little bit from the trigonometry, and it's important to understand what are called exponential and logarithmic functions. Once you get into calculus, they show up a lot. So let's start with a definition. If b is greater than 0 and b not equal to 1, then an exponential function y equals f of x takes the form f of x equals b to the x. So here you can see it's an exponential function because of the x in the power. So b is just some fixed number and x is going to vary. Here we call b the base and x the exponent. All right, so just before we get started with graphing these things, which are pretty easy to do, let's talk about the various exponents we can see on b, right? So, as we've mentioned before, for instance, consider the exponents below. Let's say 3 squared, 3 to the 1/2, and 3 to the -2. Okay? So you can see here variations of the power. So 3 squared is just as we've seen before, it's just 9, right? This is equivalent to 9. Now in calculus, a lot of the times it's important to realize that this 1/2 power is equivalent to some root, right? So if we have like this fractional power, if we look at the denominator here, this is the index of the root that we're dealing with, right? So 3 to the 1/2 power is like the second root of 3. So this is equivalent to the square root of 3. Lastly, we've dealt with negative powers before. If we raise some number to some negative power, this is equivalent to 1 over this to the positive power, or 1/9. Okay? So you can see different makeups of these powers do different things. So here, if we have a whole number power, it's just squaring out the 3. 1/2 power is the square root of 3. If we had the 1/3 power, this would be the cubed root of 3. The 1/8 power would be the 8th root of 3. And of course, when we do negative power, it's like the reciprocal of that base raised to the positive power. Okay. One more. If we have 3 to the 0 power, note that any number raised to the 0 power is equivalent to 1, no matter what. So 1,000 raised to the 0 power is 1. So knowing how to handle these different types of exponents will help us to graph the function. Okay? Just some basic laws, properties of exponents. Okay. So if a is greater than 0 and b is greater than 0, and x, x1, and x2 are real numbers, then we have some properties of exponents that we can utilize. First property, if we multiply two exponential expressions that have the same base, if we multiply two exponential expressions that have the same base but may have different powers, we can simplify this as one exponential, x1 plus x2. Right? So x to the 10th times x to the 20th would give us x to the 30th. If we divide with like bases, let's say b to the x1 over b to the x2, that's equivalent to subtracting the exponent. So we can write it as one exponential, x1 minus x2. Third property, this deals with negative powers. So b to the negative x is equivalent to 1 over b to the positive x. We just saw that in the previous example. If we raise a exponential function to a power, so we say this is a power to a power, we multiply those two powers. So this is equivalent to b of x1 times x2. And the last deal with raising a product. So if we have a times b to some power, this is equivalent to a to that power times b to that power. And the same goes for division. We have a over b to some power. We just apply the power to both the numerator and denominator. Okay. Note that powers don't really like addition and subtraction. You can't distribute a power over addition, only multiplication and division. Okay. All right, let's deal with the graphs. Graphs of exponentials. All right. So let's start off with the example. So we want to graph f of x equals 3 to the x power. Okay. All right, so note with the domain of this guy, so since x doesn't have any fractions or roots associated with it, the domain is all reals, right? Note the domain is all real numbers, no fractions or radicals there. So it doesn't matter what we can plug in any number for x that we want. So let's see what happens. Let's make a table of x, y, x, and f of x coordinates. So let's do a few. Let's do -2, -1, 0, 1, and 2. All right. All right. So let's start with the easy ones first. We'll start with 2. So here x is 2. So plug in 2 here. 3 to the second power is 9. 3 to the first power would be 3. What is 3 to the 0 power? Well, any number raised to the 0 power is always equal to 1. So just be careful with that. A lot of people mistakenly put 0 there. But 3 to the 0 power is 1. How about what's 3 to the -1? 3 to the -1, remember, is 1 over 3 to the +1, or 1/3. And 3 to the -2 would be 1 over 3 squared, which is 1/9. That comes from our properties of exponents. Okay? So I think we have enough points here to graph our function. So let's graph it. X and y. And we need to go out to a few values here. Right, So let's start plotting our points here. So 2, 9 is a point. So 2, 9, that's all the way up here. 1, 3, 0, 1. And -1 is 1/3, so right around there. And for -2, that's 1/9, so that's real close to the axis, a little lower. So we can see in this direction it grows really fast. You've probably heard the term growing exponentially. And that comes from, the graph of this thing. It just increases very, very fast. Now on the negative side of this guy, let's think about it. So we would connect those 2 points. But what happens after this point? Is it ever going to hit the axis? Well, let's think. If we were to go out to like -10, 3 to the -10 is like 1/3 to the 10th power, which is just some really small number, right? And if we continue on, it's never going to be equal to 0. So what happens is that this guy just rides along the axis, getting ever closer and closer as we go in that direction, right? So here, the domain is all reals, but the range of this guy, is from 0 to infinity, right? And not including 0, because this guy's never going to hit that axis. It's always going to be just some really small positive. So the range of this thing is going to be 0 to infinity. Now, so any basic exponential function like 3 to the x or 2 to the x or 10 to the x is always going to have this kind of range. But once we start shifting it up or down, we might be able to get an x-intercept there. Okay? Let's look at the graph of (3 to the -x). Okay? So here we can just use transformations to get it. We can use transformations of the parent function, which is 3 to the x, to get our points here. Okay? So using transformations, right? So here we're just applying a negative to all of the x values. So we're going to change all of the signs of the values in the x list. So our -2 becomes positive, -1 becomes +1, 0, -1, 2. And we have done nothing to the y's. There's no number multiplying out front. There's no addition over here for a vertical shift. So we're going to change our x's but leave all of our y's the same. So here we'll have a 9th. Here we'll have 3rd, 1, 3, and 9th. Those just come from the parent function here, right? So let's see what happens. Same idea. So now at 2, we're at 1/9. So here we're at close to the axis, and then 1/3, so a little higher. And then 0, 1, and -1, 3, and -2. So same idea, just rides along the axis in this direction. So if we compare, it just kind of flips it horizontally, or horizontal reflection here. So it just takes this graph and just flips it around, right? All right. Let's look at one more. How about if we put, instead of 3 as our base, what happens if we do 1/3 to the x power? Well, notice here that we have 1/3 to the x power. Now, how can I rewrite this 1/3? Well, isn't 1/3 equivalent to 3 to the negative 1? Well, yes, because 3 to the negative 1 is just 1/3. So this is actually 3 to the negative 1 to the x. So we have a power to a power. So our properties of exponents say that when we do a power to a power, we multiply those exponents. So here we would get 3 to the negative x again. All right. So 1/3 to the x is equivalent to 3 to the negative x. And we just graphed this guy. So we'll just say see previous graph. Okay. All right, now let's deal with transformations, some more detailed transformations of exponential graphs. Okay. So I have an example. Identify the transformations. From the parent function, parent graph, and graph the function. Okay, so let's look at f of x equals 3 to the x plus 2 minus 1. So if we recall from transformations, we have some x plus something and then minus 1 on the outside. So when we do this, we kind of look at the power as kind of being grouped here with the variations on x here. This minus 1 is outside of that, so that's going to affect the y coordinates. So here, this tells us we have a vertical shift. And which direction? That would be down 1. And then this guy up here tells us that we have a horizontal shift. And remember, it's always opposite, the opposite effect that you see when it comes to the x values. So this would be to the left 2. Okay. So, I mean, we could plug in x values and do that, but if we're using transformations, it's pretty simple to do. So let's look. So our parent function y equals 3 to the x. We had a table from previous portion of this lecture. We're going to use transformations. What are we going to do to our x's and our y's? Well, we're shifting left 2. We're going to subtract 2 from all the x's. And we're shifting down 1, so we're going to subtract subtract 1 from all the y's. So again, we're starting with the parent function 3 to the x. If this were like 4 to the x plus 2 minus 1, we would need the y coordinates for 4 to the x instead. That would be the parent function there. Okay? So let's subtract 2 from all our x's. And then we're going to subtract 1 from all our y's. So the bottom are fine. 8, 2, 0. 1/3 take away 1 is negative 2/3. And 1/9 take away 1 is negative 8/9. So we do our graph here. We actually have a 1, 2, 3, 4, 5, 6, 7, 8. We actually get a little negative here. And then we have some negatives there. All right, so let's start plotting our points. So here we have 0, 8, negative 1, 2, negative 2, 0. So we actually have an x-intercept here. Negative 3, negative 2/3. So that would be right about here. And then -4, -8/9. Right about there. So you can see that when we shift it down, we can cross the x-axis now. So that imaginary horizontal line that used to be the x-axis is now at -1, right? We shifted down. So the same kind of trend that we saw in the previous ones, it's going to just ride along this value, but it's never going to cross, right? If we continue to plug in negative values here, this is going to get ever closer and closer to -1, but it's never going to hit it. So our function looks like that. Okay. So it maintains the shape. We just have shifted it to the left and then down. Okay. There is one special type of exponential function that we deal with, and that is called the natural exponential. Natural exponential function. Okay. So the function, this is the definition, the function f of x equals e to the x is called the natural exponential function. Okay? So what's this e deal here? Well, e is just is a number. It's kind of like pi. Okay, it pops up through exponential modeling all the time. And you will see this, if you go to calculus, you will see this over and over and over again. Here, e is called the natural base. And e is approximately equal to 2.71828. This is an irrational number, so the decimal points just continue, kind of like pi. But this value is approximately equal to this number here. Okay. So we can graph values for our exponential, natural exponential as well. Okay. So to graph f of x equals 2 minus e to the negative x. Okay. So here we see the natural exponential function. And we could do this one of two ways. So let's just use transformations to get it, right? So we use transformations to do this. We need our parent function. So our parent here would be y equals what? Well, it's going to be this exponential, just the basic exponential function there. And let's put in some values. We just do -1, 0, and 1 this time. Should be able to get a good idea of that. So let's start here. What's e to the first power? Well, that's just e, which is approximately 2.71828. What's e to the 0 power? E to the 0 is 1. Anything to the 0 is 1. And e to the -1, which is 1 over e, is approximately, if we use our calculator to approximate that, is about 0.368, something like that. Okay. So if you use transformations, let's identify the transformations that are going on here. So be careful with this, right, because the 2 is in front instead of in the back. So let's rewrite this. Actually, we can just put the 2 in the back here. Remember, that's a positive, so we would have like negative e to the negative x plus 2. That's the same thing. So let's see what's happening. So we have a negative out front. So remember, the negative out front, that's going to be a vertical reflection. That changes the sign of y. We have negative x, so that's going to be a horizontal reflection. That changes the sign of x. And this plus 2 is a vertical shift of up 2, right? So let's think about what we're doing to x. The only thing we're doing to x is making them negative, right? So we would negate all the x's. So we have 1, 0, negative 1 instead. And then we're making the y's negative and then adding 2. So make sure you follow the order of operations, negative y plus 2. Okay. So let's see what we get. This guy is going to be approximately 1.632. Here, negative 1 plus 2 is positive. Negative 1 plus 2 is positive 1. And here, we get approximately negative 0.7182. Okay. So let's see what we get. X, Y. All right, so just let's plot these points. So I got a 1, a 0, and a negative 1. And not too much. So here's 1, 2, negative 1 there. So let's plot those points. 1, 1.6, be right about there. 0, 1. And then negative 1, negative 0.7. So we can see the curve kind of is curving this in this direction here. Something like that. All right. And then it just continues this way. Right? Of course, we could always plot some more points in our parent function to get those values. Okay. All right. Let's deal with finding some intercepts, and then that'll do it for this lecture. Okay. So, finding x and y intercepts. Okay. So just like with all the rest of the functions, to find an x-intercept, we plug in 0 for y, and to find a y-intercept, we plug in 0 for x, right? So let's do it. Find the x and y intercepts of the graph, if any. Because we saw that sometimes we don't have any x-intercepts there, okay? So let's look at the first one. F of x equals 2 to the x minus 4. Right? So our y-intercepts are pretty easy. So y-intercepts, remember we just plug in 0 for x. So f of 0 is 2 to the 0 minus 4. Well, anything to the 0 is 1. So that's 1 minus 4, which is negative 3. Therefore, our y-intercept is 0, negative 3. For x-intercepts, we need to plug in 0 for y. We're going to create a 0 on the left-hand side, and we're going to solve this thing. So, 0 equals 2 to the x minus 4. Okay. So to solve this guy, note that that x is kind of trapped in the exponent for now, but we can do this. This is a pretty simple one. So if we add our 4 over, 4 would equal 2 to the x, right? If we just add 4, add 4. So now if we look at this equation, what is the value of x that makes the right-hand side equal to 4? 2 to what power gives us 4? Well, that's 2. So x is 2. Therefore, our x-intercept, we only have 1, is 2, 0. B, how about f of x equals x e to the x plus 10 e to the x. So we're going to find our x and y intercepts here. So y-intercept should be simple. Y-intercept is found by plugging in 0 for x. So f of 0 would be equal to 0 times e to the 0 plus 10 times e to the 0. Okay. So this would be 0 times e to the 0 is 1. Anything to the 0 power is 1 plus 10 times 1. 0 times 1 is 0 plus 10. That's 10. So our y-intercept is 0, 10. Our x-intercept is when f of x is equal to 0. So set the equation equal to 0. Right. So with this one, we can't really solve for x explicitly because of these e to the x terms on them. So whenever we have that, factoring is try factoring and see if you get something good there. So let's look. We factor out the e to the x on the side, what do we get? E to the x times x plus 10. Right? So if you remember when we solved quadratics, we would set each of these factors equal to 0, right? So e to the x equals 0, and 10 plus x plus 10 equals 0. So you can see from this one, x is equal to negative 10, right? So that gives us one of our x-intercepts. Now how about this guy? E to the x equals 0. Well, if we think about it, this is a basic exponential function, right? So if we kind of consider the graph of e to the x, remember the graph of any basic exponential always has this kind of shape to it, right? Is this function ever going to hit 0? And that means, is it ever going to cross the x-axis? Well, the answer is no. Remember that this, if we go back, then we just ride along that axis. So e to the x is never equal to 0. So there is no solution from that. Therefore, our x-intercept is negative 10, 0. All right, so you should be able to attempt the 5.1 homework now.